And our next speaker is Ujjal Kumar Dey. We will listen about ultralight scalars via superradiance. So, yeah, over to him.
So we are trying to see ultralight scalars via superradiance effects, and we will do this by some kind of direct and indirect effects. So this is a work which I've done with my PhD student Indra and our project student Soumya. So this is the brief outline of the talk. So first I will just briefly mention what is the superradiance and what are the consequences of the superradiance and how we can generate gravitational waves as well as a neutrino flux from that. And afterwards we will just discuss how a combined messenger like the neutrinos and gravitational waves we can employ to say something about these ultralight scalars. And then we will briefly talk about some direct signals and then in some indirect effects, and then finally we will summarize. So first, coming to the introduction, so since this ultralight scalar, so UBs are ubiquitous, like ultralight bosons are ubiquitous, at least in theory. So whenever you are thinking about ultralight scalars, so the first things comes to mind is like ultralight dark matters, and for example there are so many models like that where the dark matter can be really light, sub-GeV, sub-eV even. And apart from dark matter, you also have axions, relaxions, axion-like particles, and that kind of things. That also, those kind of particles are also ultralight bosons, right? Then you can have hidden or dark photons. So they also falls under this category. And if you want to be even more fanciful, you can go to the string theory, and from there you can have moduli fields, dilatons, radions, and all this kind of things. So the zoo of these ultralight particles is quite big. Now, although ubiquitous, at least even in theoretically, but they are elusive too. And for example, there are so many experiments which are proposed. For example, for axions and axion-like particles, there are some experiments which actually employs the idea of inverse Primakov effect, where two photons can be generated from those particles in the presence of magnetic field. And there are experiments like ADMX and Haystack, which is trying to detect those particles. Moreover, these axions and ALP kind of particles also result in spin precision in atomic and nuclear systems. So some experiments in that front would be like Casper, Quarks, and this one. There are also axion helioscopes like these experiments which are trying to detect them. As far as dark photons are concerned, they are also being tried in a similar manner in various experiments. But obviously, for the dark photons also, most of the things will be similar to the normal photons, but you have to take extra precaution to shield the normal electromagnetic fields. And such kind of experiments are like dark matter radio and things like that. And for moduli, dilaton, and radion, and that kind of thing, they actually lead to some kind of variation in the fundamental constants, and they can be tested by optical magnetometers. So I saw there is one poster on this genome thing. So if you are interested, I mean, whoever is presenting that, you can get more information from that. Now, all these techniques, all these detection techniques that was mentioned in all those experiments, they are implying the electromagnetic coupling. Most of the time, it is the electromagnetic coupling, and sometimes couplings with nucleons or effective couplings with nucleons or fermions also. And apart from that, there are several indirect means have also been put forward, like the idea of cosmic birefringence and gravitational waves, etc. Now, in this specific case, we want to consider a situation where, let's say, on top of, let's say, this type of coupling, suppose the ultralight scalar or ultralight boson has some kind of coupling with the neutrino. So then, what will happen? So that is what we want to say in this thing. Okay, and in doing so, we want to employ the idea of superradiance. So first, I will just briefly talk about the idea of superradiance and what is this. So before discussing the original black hole superradiance, first let's take a mechanical analog. So suppose we have one cylinder like this, and let's say one ball is just moving, and it comes to its contact, and it touches it and goes away. So obviously its velocity will get reduced. So in this case, the loss of energy and angular momentum of this ball happens if the cylinder or the sphere is stationary, and this loss of energy is happening to the ball due to the friction or the dissipation. Now suppose we have a situation where the cylinder is rotating, okay, with some angular velocity. So if that kind of thing is happening, then obviously the ball's kinetic energy will get enhanced, okay. So that means the energy or angular momentum can be extracted from that rotating cylinder, provided some conditions are met. So this kind of conditions, for example, if this kind of conditions are met, then we can have some kind of extraction of the energy and the angular momentum from that rotating body, okay. And obviously in this case the dissipation actually leads to the enhancement of the kinetic energy of the outgoing body. Now you can think of a wave analog of it, okay. So by wave analog of it, suppose we have a rotating cylinder and we have some kind of incident wave. So incident wave on rotating dissipative surface also can grow in amplitude by extracting energy and angular momentum if again these kind of conditions are met. So in this case, this capital omega is the angular velocity of this cylinder, and omega, small omega, is the angular frequency of the incoming wave, and m is the angular momentum along the axis of the rotation. Now again, for the wave analog also, you can think of this as a mechanism for extracting energy and energy from a spinning compact object. And in nature we have such kind of objects like our spinning black holes, okay. Obviously for the spinning black hole, the geometry of spinning black hole can be described by the Kerr geometry, and if you the geometry of the Kerr black hole is a bit involved, but you just take this, that we have two kinds of horizon there, like some kind of outer horizon and some kind of inner horizon, and in between the region is called Argo region. So now black holes which have non-vanishing spin can also trigger such kind of superradiance, okay. So that means the incident radiation field can be amplified by extracting again energy and angular momentum, okay, from the black hole. And during this process, the mass and angular momentum of the black hole can change. And in this case, the condition for the superradiance to occur is like this, and here this omega h can be written in terms of the parameters of the Kerr metric, normally which is written in the Boyer-Lindquist coordinates, and in that coordinate you can write this omega like this, okay. So if this condition is met, then we can have this superradiance effect for the waves. Now here till now I was thinking about the wave, let's say some kind of field, electromagnetic field or whatever. Now suppose you are considering some kind of field again in this kind of wave format, let's say they are massive. Then what will happen is that then in the gravitational potential it can get trapped, and it can keep on increasing its amplitude, and it can keep on increasing its keep on extracting the energy from that black hole. And at certain stage what can happen is that, I mean, if this condition is met actually, so if the Compton wavelength of this waves is larger than the or let's say of the order of the radius of the black hole, then there actually some kind of instability kick in, and then we can have some kind of scalar cloud formed surrounding that black hole, okay. So it will somewhat look like this. So if you want to calculate this, so what we have to do, so you have to take the Kerr geometry and you have to write down the scalar fields and everything in the equation of motion, and everything will now get changed, right, according to that geometry. So once you have that equation of motion, then you have to solve those equations, and then you will get to know the dynamics of all this setup. And if you do that, again, I mean, since this kind of gravitational systems are really non-linear and all, you have to employ some kind of approximations, and in those approximations you will be able to see that the ultimate wave function of the scalar field that is surrounding that black hole will follow a wave function almost like the hydrogen atom, okay. That is why sometimes you can call this kind of cloud like some kind of gravitational atom, Okay, and which is almost analogous to the electron in the hydrogen atom, and with discrete energy levels. Okay, and there also you will be having the quantum numbers like n, l, s, that kind of thing. And the efficiency of this whole process can be dependent on the gravitational fine structure constant, which you can define in this manner. So if this alpha g, which is the gravitational fine structure constant, if that is let's say order 1, then this effect would be the best, and if it is lower, then the effect will not be that good. And so this is one parameter that we are going to use. And also you see that depending on what kind of masses of the black holes you are considering, what kind of ultralight scalars or ultralight bosons you can generate from this super radiance mechanism has a range. So the range is something like this. Moreover, the mass of the cloud that will be formed here can be approximately given by this, and from the numerical gravity simulations, it can be shown that the mass of this cloud cannot become larger than the 10% of the total black hole mass. So, to summarize, this superradiance effectively extracts mass and angular momentum from the black hole, and this process of superradiance effectively reduces the spin of the black hole. Okay, and if you have some kind of astrophysical observations of black hole with spin, then you can put bounds on the this kind of ultralight boson. So previously this was done, and very recently Ranjan and his group used this Sagittarius A star data and put some bound on this kind of ultralight scalars as well. So again, when we are talking about extracting mass and angular momentum and energy, this kind of thing, this Penrose process is something that might ring some kind of bell in your mind. So let me just briefly say this, that you can think of superradiance as a subset of this kind of Penrose processes. So Penrose processes are what? So they are processes in which black hole releases energy, angular momentum, or charge by increasing its horizon area. So there can be different types of Penrose processes, like particle splitting in the ergo region, or this Blandford-Janacek effect, which is actually a superradiance kind of effect, but with electromagnetic waves. And actually the astrophysical jets for the supermassive black holes that we see, that is explained using this effect. And then we have the superradiance. And when we are talking about superradiance, we are mostly talking about the rotational superradiance, which is, you can think of as a stimulated or spontaneous radiation enhancement mechanism by which, again, energy and momentum is extracted. Okay. Now, once we have that scalar cloud kind of system formed around the black hole, then we can generate. Then that kind of system can generate gravitational waves through different mechanisms. For example, the ultralight scalars or ultralight bosons that form that cloud can annihilate to gravitons, so that can lead to some kind of gravitational wave spectrum. Or, for example, there is some kind of transition between the transition of the energy levels of that gravitational, that also can lead to some kind of gravitational wave spectrum. And the most interesting one is the abrupt collapse of the cloud in the presence of some kind of self interaction, and this is funnily called as some kind of Bose nova in the spirit of supernova. So anyway, you can look at these references for some detailed discussions about this kind of emissions of gravitational waves. Now, as I said, that there are three main ways that gravitational waves can be generated from such a system. Depending on what kind of processes are dominant, these gravitational waves can be either transient or can be stochastic in nature. So that means whether they are those gravitational waves are lasting for a finite time or they are of stochastic nature. Now, for simplicity, again, for our as I said, so our analysis is not very rigorous or so. We just wanted to test this idea. So here we are just considering the case of the annihilation of the scalars into gravitons. Obviously, the ideal case would have been the comprehensive analysis by taking into account the all black hole population throughout the all sky, and consider the entire population of the black hole into account, and incorporate all possible sources into the analysis to predict the resultant gravitational wave spectrum and do work on that. But here we are not doing that, at least not here. Now, another way of another step of simplicity that we are using is that we are considering the transient monochromatic gravitational wave that can be generated from this kind of annihilation, and the energy release from that energy release in the form of gravitational wave can be given by this thing. I think there is a typo. This MSU should read as M phi, and MBH is just the mass of the black hole, and alpha G is the gravitational fine structure constant that I already discussed. This 4L and 4S are the quantum numbers, because I already mentioned that it will follow a hydrogen atom kind of setup. So this will give you the rate of energy release by the energy release in the form of gravitational waves. Also, you can do some back of the envelope calculation, and you can get some other relevant parameters, and you can estimate them, like for example the frequency of the gravitational wave or the strain of the gravitational wave expressed in terms of these parameters by these forms. Okay. Now this was the part where we generated the gravitational waves from that superradiant cloud. Okay. Now the next step is, if we have the neutrino coupling like this. So let's say we have this kind of effective coupling like this, then it is possible to generate a neutrino flux from that ULS cloud as well. So how are you going to do that? But before that, remember that this kind of coupling is already constant from supernova consideration and CMB data and things like that. So in our study, we always want to remain within those bounds. So let's say we will be taking this coupling to be of the order of 10 to the minus 8 or even less. Now, due to the presence of this coupling, what happens is that due to the presence of this coupling and this background field phi, the neutrino mass, the effective neutrino mass becomes oscillating, and it becomes of this form. And then under certain conditions, some kind of resonance conditions are met, and then the physical neutrinos can be produced. And again, I mean, this is somewhat like the discussions that you had in the pre-lunch session, right? That particle production thing, particle production during that preheating region. But it is also somewhat similar to that. So those kind of assumptions or those kind of simplifications that you guys were discussing, so those are already embedded in here. But the main point is that by that kind of parametric resonance, you can generate these neutrinos. And once you have generated those neutrinos, then they can begin their propagation in this cloud following the constant geodesic equation there. And you can do some algebraic calculation, and you can come up with this equation for the energy of the neutrinos and the flux of those neutrinos, which will mostly look like this. So now that you have the form of the energies and flux of the neutrinos, and in the previous slide I showed the gravitational wave spectra as well. Now what you can do, you can have a combination of these two things and see how everything plays out. So before discussing the direct signals with some benchmark points, obviously, note how the basic dependencies of the two messengers plays out. So these are this you can think of as the dependencies of this of, let's say, the E nu and the frequency of the gravitational waves, and let's say this is the flux and the gravitational wave strain with this kind of parameters. So benchmark cases that I wanted to discuss is something like this. So for example, let's say these are the black hole masses that we want to consider. So let's say 100 solar mass, this solar mass, this solar mass. So in choosing these benchmark parameters, we just thought that maybe some astrophysical black hole kind of parameter, some PBH kind of parameters, or some supermassive black hole kind of parameters. So it is just like that. And in choosing the distances also, we remain conservative, so that none of these black holes are like within our visible range or something like that. And if the ULS, the ultralight scalars that will be formed out of this BH that you want to calculate, so that you can quickly do by noting the alpha G value, because alpha G is related to the MBH and M phi. Okay. So once you have that, then from those benchmark points, you can have this kind of distribution of those points. For example, if you want to see the gravitational wave strain versus frequency plot, so obviously all of you know that these are the experimental reaches of the various experiments. So all the benchmark points, you can see that in some of the cases we can have within the reach of some of the gravitational wave detectors. And in case of neutrinos, you can see that some of the benchmark points will lie, obviously all of them will be in the highest energy possible regime. In some cases it will be below, let's say, the atmospheric flux, and in some cases it can be towards the cosmogenic fluxes. So for example, if you ever see some events in that range, so it can be thought of as some origin from that kind of thing. Now obviously, so that kind of multi-messengers, meaning gravitational wave neutrino thing you can do, but additionally there will be some indirect effect of that coupling that I was mentioning, the G phi nu bar. So that kind of coupling can lead to decay of the neutrinos of this form, and if we have that, then that will have some implication in the C nu b, cosmic neutrino background. And Ptolemy is the only experiment that is trying to detect this C nu b's by means of this neutrino capture on tritium. And ultimately this Ptolemy experiment is trying to measure this electron spectrum, and from there it is trying to measure the C nu b. So if we do that, so we are going to get an electron spectrum like this. So here this is the normal beta decay background thing that you can get, and this yellow and green are the peaks that you usually get in this kind of study, depending on whether you are taking the normal hierarchy or inverted hierarchy, depending whether nu3 is the highest mass or nu2 is the highest mass. So you will be having 2 or 3 different peaks. So in this case, you can see that you will have a typical spectrum, typical electron spectrum like this. So obviously here we took just one of those benchmarks that I mentioned, and the other benchmarks will also look similar. Note that solar neutrino experiments are not sensitive to couplings less than this, and long baseline experiments are not sensitive to couplings less than this. Since in our case the couplings are very small, so this is just the I think the only way to test this kind of setup. So that's all, I'm done. So just to summarize, so we have spinning black holes, and that spinning black holes in the presence of superradiance can give rise to some kind of ULS cloud, and that ULS cloud can give rise to neutrino flux as well if you have the ULS and neutrino couplings. And the ULS cloud itself can give rise to some kind of gravitational wave, so that you can think of as a direct signal for this kind of setup. And if you have neutrino decays by means of this kind of coupling, that will modify the C nu b spectrum, and that you can take as some kind of indirect signal. So you can have this kind of signals for this kind of setup. So that's all. Thank you.
Yeah. Thank you. Yeah. Questions?
Yeah.
Maybe I can.
No, for other persons.
Ujjal, since you are looking at coupling of a light mediator with neutrinos, you might have other constraints, for example, an effective for neutrinos.
Yeah, that's what I already told you, that those bounds I already become conservative enough to keep all those couplings or all those masses to be way less than whatever those bounds are.
What's the typical coupling strength?
So the 10 to the minus 7, for example, from CMB data or from supernova
I'm
cooling.
not sure that is low enough.
That is low enough. So okay, so what are the couplings?
The constraints can be lower, so we can discuss it later.
Okay, from which point of from which consideration?
The thing is that you have light mediators, so they can change an effective, and the constraints on coupling can go to 10 to the power minus 9.
Okay, that's fine. And as I said, so these are some benchmark points. I can tune
maybe
those as well. Yeah. Okay. Yeah. Yeah.
Okay. Yeah. I mean, LIGO has already searched for these line-like gravitational wave spectrum.
Search for what?
Advanced LIGO has searched for this line-like gravitational wave signal from superradiance. So that may be constraining some of this where you showed this.
But that will give bounds on those as.
It will not give bounds on the coupling, but it will constrain those masses, right?
Okay.
Phi goes to 2 GW. It's a line that, as far as I remember, LIGO has searched for this.
Okay, so
can say.
Okay, I'm not aware of it. I have to check. So this is when is this?
When?
I mean this study that you were talking about. When I am not aware of it.
After should we last 3-4 years? 2-3 years?
2-3 years. Okay, I have not seen that. Okay, I will check.
Yeah, I think so. But
that will put some bound on the from the BH masses, right?
Yes. So they will assume some supermassive black hole or something like that, and then you have a monochromatic or intermediate mass astrophysical black hole population. Then you have a monochromatic signal. I have seen either talks or papers.
Okay. I will see.
Something.
Yeah.
So one naive question. So when you showed this wave analogy of reflecting of a spinning ball, I would have expected a Doppler shift, but you were always saying increase in amplitude. So maybe I don't know the.
No. Obviously, that has to be taken into account. So in this kind of study, I think this the correction to the redshift correction is taken into account by that with the frequency you will just multiply 1 plus Z factor, and that will be taken into account. But what you are saying, I think I'm not sure.
Okay, thank you.
Yeah.
I don't know if this is a naive question, but 1987A supernova data will be of any consequence here, since you're...
that's what I've said. That 1987A that gives some bound on that coupling actually. That is I think 7 into 10 to the minus 7.
Okay. Yeah.
Yeah.
Thank you.
Yeah. So let us thank him again.